Hello, thank you for watching our presentation. My name is Abby.
I'm Michael.
I'm Tim.
I'm Jonathan.
And our project is the delay-based physical unclonable function. Our advisor is Dr. Tehranipoor. Here is a quick outline of our presentation. I'll start us off with the problem and some background information. Technology is improving at an impressive rate. Transistor count, IC complexity, and overall circuit usefulness have increased tremendously over the past few decades. However, since then, silicon wafer production has shifted abroad mostly. TSMC, or Taiwan Semiconductor Manufacturing Company, holds around 50% of the market share, and the silicon produced needs to be shipped to the US, creating the opportunity for maliciousness in the form of counterfeiting and IP piracy. There's a need to verify that the silicon made at the foundry is the silicon received, and also to discourage the future reverse engineering of the ICs and theft of intellectual property. Upon first inspection, a counterfeit chip may seem legitimate. Of the two 80 mega ICs seen in the top right photo, the chip on the right is fake, and it can be extremely difficult to tell the difference. These counterfeit parts are typically less reliable, and problems may not arise until well after the part has been installed. Around 15% of the chips that the Pentagon receives are counterfeit. Some counterfeit ICs can even find their way into places such as nuclear submarines. ICs need to be authenticated to be absolutely sure that the chips received are legitimate. One way of doing this is by using a physical unclonable function, hereon referred to as a puff. A puff is a circuit that takes in a bus of inputs called a challenge and returns a bus of outputs called a response. Together, these are referred to as a challenge-response pair, or CRP. On two different ICs, the puff subblock will have the same schematic but produce a different set of CRPs, acting as a sort of silicon fingerprint. A puff ideally has an unpredictable but static output. Metrics that are used to measure a puff's performance are randomness, reliability, and uniqueness. To get an idea of what I mean when I say randomness, uniqueness, and reliability, imagine a silicon wafer. On that wafer, let's take two of the ICs and look at the puff part of the circuit. If we give the puff a random challenge and look at the output of one of them, ideally, there is no correlation between the challenge and the response. Another way of saying this is knowing only the challenge, we should be clueless about the response, and no amount of data analysis will make a different puff's response any more predictable. This is what we mean by randomness. We gave the second puff the exact same input, and if we look at the outputs, they should not be the same. When a puff is manufactured, we roll the dice and generate a new set of CRPs. Given the massive range of inputs and outputs of a puff, it is practically impossible for one puff to have the exact same CRP data as another. This is what we mean by uniqueness. Finally, if we were to retest the puffs with the same challenge, ideally, we should get the same response as when it was tested the first time, even considering use and any environmental variations. This is what we mean by a static response, which is our measure for reliability. Reliability is measured as a percentage, where a higher reliability indicates better performance. The ideal reliability of a puff is 100%, meaning consistent CRP data for the puff across all variables. Hamming distance, represented by the HD in the equations, simply means the number of bit differences between two bit strings. Uniqueness is measured with the interhamming distance, which is the number of bit differences for two different chips given the same challenge. The ideal value here is the number of bits divided by 2. Finally, randomness is measured by the Shannon entropy of the CRP set. A higher value here indicates a less predictable response and therefore a better performing puff. I would like to hand it over to Michael to explain our senior design project objectives, project plan, and the block diagram of our design puff.
So our project objectives were to design, simulate, compare, and post-process the data of a delay-based ring oscillator puff on an FPGA board. This includes two different schemes. We'll call them serial and parallel. I'll explain them later. We have an 8-bit ID, which means 8 bits in, 8 bits out. We'll optimize for reliability, uniqueness, and randomness, and we will not be worried about manufacturing, supply voltage variation, or temperature variation. Two things to note here. One, 8-bit ID is kind of small. It can be easily brute forced. However, we're purely looking at proof of concept. We're not worried about the size, or just worried about the statistics afterwards. The second thing is, if we're not manufacturing, how do we actually test a circuit that requires physical variation? And that's where the FPGA is useful. The FPGA gives us that physical variation that we need without us having to spend a lot of money on actually designing and purchasing our own ICs. So here we have the general schematic for a ring oscillator-based PUF. Pretty much every design starts with something that looks like this. We have a ring oscillators group on the left. A ring oscillator is just a loop of an odd number of inverters. Since it is an odd number of inverters, each node oscillates between a logic 0 and a logic 1 at some frequency. These ring oscillators feed into multiplexers, the muxes, where 2 are selected based off of the challenge bits, fed into the selection bits of the muxes. These 2 ring oscillators are fed into their own respective counters, and the first counter to reach some predetermined value indicates that that ring oscillator is faster, and therefore we can generate either a 1 or a 0 from the entire circuit based off of that. One thing to note is that no matter how many ring oscillators we use in the left, and therefore how many challenge bits we need for the muxes, we only generate 1 output bit. So a lot of our work and thought process went into how do we generate more output bits using something like this. Our project plan was to mostly do research in fall quarter, looking at and read papers and kind of get ideas on how to design a ring oscillator-based PUF and start testing it. We were going to start simulating and prototyping these designs in Verilog in fall. We would put them onto an FPGA in winter and begin to actually collect data in winter, and then do data analysis in spring. So for division of labor, Abby did a lot of the initial work with the parallel scheme, and she has also done most of our Python scripts for data processing after we've already collected it. Tim has done a lot of the work around the test setup. He's designed the entire FPGA interface that we use to send challenges and receive responses. I personally did a lot of work with the serial scheme, both the high level and some of the Verilog. Johnny has done Verilog for both schemes, and he has also collected most of the data for us since he has ended up with our equipment post-COVID shutdown. So here we have our parallel design. On the left, you can see that first initial design that I kind of went over. There's not really any change made there. On the right side is our attempt at generating more output bits. And while inelegant, this method is certainly effective. We took that block, replicated it 8 times, and now we have 8 output bits. We can reuse the same challenges into each subblock. Since each subblock uses its own group of ring oscillators, we expect this to be very random and very unique, but there's obviously a huge hardware overhead, especially if you were to use a more realistic size, such as 128 or maybe 256. The hardware cost for this would get very, very large. So our next circuit, the serial scheme, kind of combats this hardware overhead. You can see that we've taken that first design and we've added 2 blocks outlined in the yellow, our scrambler and the buffer. The scrambler is fed in 1 8-bit challenge input and generates 8 serial 8-bit challenges. In this way, we cut down on the hardware use because we can reuse the same ring oscillators and the same counters and muxes. However, this should be a lot less random, or not a lot less, but this should be less random and less unique than the parallel scheme because we have to use ring oscillators. The buffer simply collates 8 sequential outputs into one group for us to look at later. So when we were designing this scrambler, we had a few options. Some papers have done serial schemes before, and we'll kind of talk about what they've used. A lot of papers have used circular shift registers. These are, I will say, bad choices because they have lots of quote-unquote bad challenges. By bad challenges, any challenge with a pattern results in a response with a pattern. This makes things very predictable and leads to very low entropy. A counter is another common option. This is a much better choice because it removes the bad challenges. There's no issue of patterns. However, you do have what I'm calling adjacency issues. Since a counter is very linear, it always counts from 0 to 1 to 2 and so on. That's what a counter does. That means if you know the response generated by an input of 0, you know a significant amount about the response generated by an input of 1. the adjacent inputs share a lot of the same response data. And so we kind of needed to combat this. So the first step we did was to introduce a linear feedback shift register, an LFSR, instead of a counter. This LFSR runs through the same input space a counter does, but in a pseudo-random order. However, it still has the adjacency issues. It just simply shuffles them around. So the next step we did was to add nonlinear behavior into this LFSR, and we deemed the entire block a scrambler. And the scrambler takes the initial challenge that we sent in and XORs all of the LFSR outputs with that initial challenge to create this nonlinear behavior that no longer has any sort of adjacencies that the counter suffered from. Right here, you can see a screenshot of our synthesized design in Xilinx Vivado. You can see the two groups of 16 ring oscillators on the left, which feed into muxes, and then the counters and the race arbiter, along with the buffer. And right there in the center is the scrambler. And now I will hand it off to Johnny to talk about our hardware setup and some of the challenges we encountered during design.
So jumping right into it, this is our system hardware setup. And really the motivation for coming up with this whole design or this whole sort of infrastructure was that we wanted to automate the collection of data, but have the ability to do so without sort of having to give our project the full attention. So in a sense, we could basically collect data, 24/7. And so the basic setup is that on the left, you'll see the Raspberry Pi, and we take an 8-bit gray code file and parse that file line by line, get the challenge, and we then send that challenge to the FPGA, which then sits on top of the Digilent RD S7 board, pictured on the right, through the GPIO interfaces on both systems. And so this is the actual picture of the hardware setup. And below that is a state diagram with two states. And this really dictates the control logic of the Raspberry Pi. What's happening underneath the hood is that the Raspberry Pi is sending a challenge and waits for the FPGA to generate a response. Once a response is generated, a done signal is asserted, and the Raspberry Pi then knows to store that response, sends a new challenge, and then resets the FPGA, and it cycles through those two states again and again. And so throughout our project, we had a number of design challenges, the first of which is the inability to simulate actual hardware, right? When we were simulating our design in the early stages with a tool called Synopsys VCS, we realized that there was really no way we could actually simulate that random, hardware, right? And so, but it is something that Vivado can do when you actually get it onto the FPGA. And so this sort of need to simulate random delay pushed us to get our design onto the FPGA fairly early on. One other thing to note also is that we were considering Monte Carlo simulations as well. But much as we really wanted to do them, we realized that there was no way to actually perform these kinds of simulations on a digital logic circuit. Another kind of design challenge that we ran into revolves around HDL code optimization, right? This is hardware description language code optimization. And so oftentimes when we're using, electronic design automation tools like Vivado, optimizers are built in part, and they're usually your friend. They get rid of logic that is not being used. And so what you currently see is a snippet of Verilog code for the ring oscillator. And there are 15 wires that are instantiated. Each of them are defined as the invert of the previous wire. And so in this case, the optimizer believes that the 15 inverters is logically equivalent to one inverter, which is sort of evidenced by the lack of blocks that you see in the schematic. And it's not necessarily wrong in doing that. It's just not what we want, right? We actually want the delay to be there. And so with the help of Pat from Xilinx and his team of application engineers, we were able to make a small but fundamental change, which is the addition of the don't touch directive outlined in the red box. So now, as you can see, the synthesized schematic now displays all 14 inverters with one NAND gate, which is what we wanted originally. Another design challenge that we came across was in the creation of the infrastructure for data collection. So I talked about the system hardware setup earlier, in which we used a Raspberry Pi, but it didn't always used to be like that. One of the first things we thought of when attempting to automate data collection was to use an Arduino. A big downside towards this approach was that the handling of the serial port was quite unwieldy. You have to open a serial port on the computer side, also on the Arduino side. And then there were a number of dropped bits as well happening during transmission. And as well as another worry, which was that the GPIO pins on the Arduino operate at 5 volts, which is much higher than the 3.3 volts that the FPGA accepts. So the other alternative, that we tried and of course ended up adopting, and in hindsight this was a clear choice, was the Raspberry Pi. And it was definitely a much more elegant solution. Firstly, it outputs 3.3 volts, which is perfect for the FPGA, as well as from the comfort of Python, we're able to send and receive challenges, right? We don't have to go down into the low level C that we did on the Arduino. And so that was really, that's basically our design decision on why we decided to choose the Raspberry Pi over the Arduino. During our initial bring up of our automated testing environment as well, one of the other big issues we encountered was timing. If any of you are familiar with the problem of clock domain crossing at all, this is that classic problem, although more at a system level. And so what's happening is that the FPGA outputs a done signal, that's the waveform on the bottom, that is high for one FPGA clock cycle, but since the clock on the Raspberry Pi is too slow, evidenced by the sort of longer period, that the done signal is essentially never latched. And so we solved this in 2 ways. First, we increased the counter value, and all the way from 2 to the 8, all the way to 2 to the 22nd. So from about 256 to about a value of 2 million. And so you can sort of think of this as slowing down the frequency of the FPGA clock, allowing that signal to actually be latched. Secondly, and this is probably the more important change, is that we've essentially changed the done signal's behavior in such a way that that signal will assert for forever until a reset is sent from the Raspberry Pi. And so in other words, what we've done is we've made the done signal a sticky bit. And what that accomplishes is the creation of a handshake between the Raspberry Pi and the FPGA. And this is reflected in the state diagram that you saw earlier in the system hardware setup. Next, Tim talked about the uniqueness metric earlier, and one way to actually measure this is to manufacture different chips. But another alternative, a cheaper alternative, is to purchase many different FPGAs. Cheap as it is, as students, we're not at liberty to make those kinds of purchases. So to get the most out of our FPGAs, we basically placed our design in different spots within the FPGA, essentially simulating different chips, right? Different placements, meaning different puff instantiations on different chips. So again, with the help of Pat and his AEs, we were able to specify in a constraint file the specific slices that we wanted to place our design in, sort of evinced by the first and second pictures. And then the rightmost screenshot is the parallel scheme. And as you can tell, that takes up much more space on the die than the serial scheme. And of course, this is to be expected. And finally, when we're comparing both parallel and serial schemes, the reset logic in the parallel was much easier because it was all handled by the software in the Raspberry Pi. But once you start to serialize, there has to be some notion of resetting this circuit. And so really the challenge was, how do we write the Verilog such that, we elaborate the design properly and make sure we get the behavior that we want. And next to talk about, next we'll wrap up some of the project outcomes. We'll talk about the project timeline, as well as some of the conclusions that we can draw from the data that we have analyzed. And to tell you all about that is Abby. Abby?
These are our reliability results of the 2 schematics. Reliability measures the difference in the response bits when the same challenge is given to when the same challenge is given to the same puff. The ideal reliability is 100%. The parallel scheme has an average reliability of 99.65%, and the serial scheme has an average reliability of 99.45%. These are comparable to many of the ring oscillator puffs on the market right now. Reliability increases when the differences in the frequencies are higher. Since the parallel scheme has more ring oscillators to choose from, it is more likely to have higher differences in the frequencies. Here are the uniqueness results. To measure the uniqueness, we measured the interhamming distance. This measures the difference in the number of bits in the response given the same challenge on different chips. The desired number is 50%, so a 4-bit difference. Our parallel scheme has a mean interhamming distance of 46.4%, and the serial scheme has a mean interhamming distance of 62.7%, which is a bit high. Since we have 8 bits, this means that about 5 bits are changing on average. For future work, we'd like to do more testing of our serial scheme on more FPGAs and different types of FPGAs to see if this is a design flaw or something wrong with our testing protocol. Here are the randomness results. To measure randomness, we calculated the Shannon entropy. This is the Shannon entropy per bit. We would like to see a higher entropy, meaning that it is more random. The parallel scheme has a higher entropy per bit of 0.925 roughly, and the serial scheme is a little lower with 0.796. This makes sense as we are using more ring oscillators, which will give us more randomness. Every new piece of hardware we use adds a new chance for different physical characteristics to show up. This makes it so our parallel scheme is more random. Here is an evaluation table of all the numbers that I just talked about. As you can see, the parallel scheme outperforms the serial scheme in every way. However, the parallel scheme has the number of bits squared number of ring oscillators, which takes up a huge amount of hardware. The serial scheme, in comparison, only has the number of bits ring oscillators, so n bits in the serial scheme has n ring oscillators, while the parallel scheme has n squared ring oscillators. But the serial scheme still performs pretty close with the reliability and the randomness. For the future, we would like to see if with more testing and if some design changes could get us closer to the parallel scheme results with our serial scheme. Here is our final project timeline. During the fall quarter, we did a lot of research as we did not know anything about puffs when we started. We also started on writing the Verilog for the designs. During the winter quarter, we designed our test setup and did a lot of debugging. Since we were not able to simulate, we ended up spending more time than we expected debugging during the winter quarter. We were planning to do temperature and aging testing, but could not since the labs have closed. However, during the spring quarter, we did a lot of data processing and data collection. In conclusion, we found that these ring oscillator puffs are an effective means for authentication. They performed well for reliability, randomness, and uniqueness. We have also seen the parallel scheme is a good benchmark for other schemes since it has high entropy. However, since the parallel scheme has a much bigger footprint and requires a lot of hardware, it becomes less practical to place in a chip and better for use as the benchmark. The serial scheme we found to not perform as well as the parallel, but it is close and uses significantly less hardware. For future work, we would like to do additional testing on more and different types of FPGAs. We currently have a paper under review. It is called A Systematic Approach for Internal Entropy Boosting in Delay-Based RO Puff on an FPGA. The authors are us, Professor Yan, and Professor Tehranipoor. We submitted it to the IEEE Midwestern Symposium on Circuits and Systems. The conference will be held in August of 2020. Lastly, we would like to thank everyone who helped us with this project. First, Dr. Tehranipoor, our advisor, for teaching us everything we know about hardware security. Pat McGuire and Xilinx for giving us the FPGAs, and also for helping us get the most out of our FPGAs with the help of his applications engineers. We would also like to thank Professor Lewis for giving us digital design advice, the School of Engineering for funding, and lastly, IEEE Santa Clara Valley Circuits and Systems Society for giving us funding and an opportunity to get industry mentor feedback. Thank you so much for listening, and these are our references.